This video should serve as a tutorial for how to do this friction lab. This is a little bit different than the pivot labs we've done before, where instead of collecting data from a pivot video, we are using an external website in a computer simulation. Now we decided to do it this way so that all the labs are still within the pivot ecosystem that you're used to dealing with, and you're not having some labs that need to be turned in on pivot, some labs that need to be turned in on Google Docs or on Canvas through Google Docs and the like. However, the process should be roughly the same thing. So for this, below this video, you will have a window that has the lab activity you'll be doing. Underneath, you are going to have a data table. Now for this video, or for this lab, we decided to pre-populate the data table, including doing the calculations for you, as well as pre-populating the graph. So this should have all the instructions filled out. There should not be issues. And then below are going to be 5 questions, I believe, that you are going to answer. So what you are going to do is you're going to first hit begin. Now, this is a a simulation of what we would normally be doing in class. So it's using, shows using the vernier sensors that would be using on a daily basis, all of that. Now, what you can change here is 2 things. You can change the type of surface, and you can change the mass of the object. And what you're going to do is I have 3 set surfaces you are going to do. So you're going to do rubber on ice, you are going to do graphite on graphite, and you are going to do rubber on concrete. So those are the 3 surfaces you are going to do, not necessarily in that order. Now, what's going to happen is once you've selected your surface and once you've selected your mass, you just hit start and they will still start pulling on the force sensor. Now, as I said, this is a simulation of a lab you could physically accomplish. The goal here is as you pull, the sensor is reading the force that you are pulling with. Now, at first, you will notice that the object is not moving. And if the object is not moving, then that would mean, let me turn on annotation here, that would mean that you would be at equilibrium. So the net force would add up to 0 because you're not moving. That means you're not accelerating. Excuse me, you're not accelerating. Your velocity is 0 and it stays 0. So what that means is at any given point until it starts moving, the applied force that you pull with is equal and opposite to the force of friction that is resisting. Now there's still normal and that will be equal and opposite of gravity, but that is not playing a role right now. Eventually it will start to move. And when it starts to move, the simulation here, will pull that object with a constant velocity. And if you're at a constant velocity, you also are at equilibrium because your acceleration is 0. You are moving with a velocity, but that velocity is constant and therefore your acceleration is 0. So the force you are pulling with at any given moment is equal to the force of friction. Now here's why that is important. What you will see, sorry, let me clear the screen here. What you will see is when you scroll, you'll hit start. Now you'll see a bunch of data up here. You don't have to worry about what the actual little computer screen says. I understand that's very hard to read and that is not important because what you're going to get when you scroll down is a force versus time graph. This drop, so you'll see you have a diagonal line up until this point here, in which case it drops down to this horizontal line here. The top of the diagonal line, this is when the object is not moving all along those diagonal lines. So you keep pulling, 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 pulling until you have overcome what is called static friction. Static friction is the force that is keeping an object from moving. And your maximum force of static friction, which you are asked to find, is this value right here, the top of that diagonal line. Now that is going to require some level of estimation. If you need to actually physically like hold a sheet of paper up on your computer screen to get that diagonal, I know you guys all can't draw on your screens, but I would say that my value right there would be somewhere in the neighborhood of about, let's see, 0.6, 0.7, 0.8, 0.9. So like 0.9, we'll call it 0.95. Go to the nearest hundredth, or is that, yeah, hundredth. then I'm also asking you to find the kinetic friction. And the kinetic friction is this horizontal line here. So do your best to, and again, there's going to be a little bit of estimation. You'll get a nice horizontal line here. And I would say that for this mass at this type of surface, my kinetic friction was about 0.7. So what I would do is on my data table, I would say that for rubber on concrete, at an object mass of 100 grams, I have a force of static friction of 0.95, and I have a force of kinetic friction of 0.7. So I would go down to my data table. Now I'm only doing one surface at a time. So this would be, I'd collect all my data for this particular type of surface, which I'm doing as rubber on concrete. So I would type in my mass. Now I do ask you convert the kilogram or the grams into kilograms. You just divide by 1,000, which means you just put a decimal place in front of the number. 100 grams is 0.1 kilograms. It will automatically give you the normal force. And I said my maximum force of static friction is 0.95, and my maximum force of kinetic friction is 0.7. I would then go ahead and continue doing this for more masses. So if I did this, so you would just hit reset, select some different mass, doesn't matter what, just you need 6 different of them. So it's up to you. I hit start, and then I would let it run for a second. And now I can go down and find my maximum static friction, and I can find my kinetic friction. There's going to be a little bit of error here because there is going to be a little bit variance of where you think the center point is. That's okay. So you're going to collect 6 masses for each combination of surfaces. Once you are done, so you found your 6. I will make sure I include the one more table that should be here. Once you found your 6, you're going to get this graph of maximum static and kinetic friction. You are going to do a curve fit for both, a linear curve fit for both. Now it's going to look terrible because I only have one data point because I'm not doing the lab for you. And then you are going to take a screenshot, and I included pictures below of this entire graph. So the area you would take a screenshot of would be this whole thing right here. You need to include the entire graph, and you need to include the 2 curve fits below. Once you've got that screenshot, again, I included directions below, you are going to insert that screenshot into, here would be graphite on graphite, here would be rubber on concrete, here would be rubber on ice. So once you get your data, you take the screenshot, you input it down here, you then go to this data table, delete all your data, and do this again for your other 2 remaining surface types until you've got all 3 graphs. Answer the 2 questions at the end, and you are done for this week's lab.